Welcome to video 3.2 on quantum theory. Remember, when we say quantum theory, we're really talking about electrons. So in this video, you're going to be able to explain the wave-like properties of electrons and how those electrons exist in an atom. Also in this video, you're going to understand the basic principle of quantum theory, and then also evaluate the concept of quantum numbers and how they determine the probable location of an electron within an atom. Here are the vocabulary terms that you'll be hearing in this video, and again, if at any time you need to stop the video and Google any of these terms. So we already said that a lot of what we understand about electrons comes from the experimentation we've done on light. And we've already looked at how light has this wave-particle duality. Well, this professor, Louis de Broglie, created an experiment called the double slit experiment, where he shot tons of electrons through two slits in a piece of metal. Then on the other side, he had a detector plate to determine the reading of how these electrons behaved once they passed through these slits. Now, according to classical physics, we would have accepted these particles to just carry straight through, and like throwing tons of baseballs through these slits, we would have had detections in just two single slits right behind each of the slits in the metal plate. So what we should have saw, according to classical physics, is just two lines here, but instead what we saw was a bunch of lines here, a bunch of readings, a bunch of electrons were detected in these patterns. This is called an interference pattern, and this shows how electrons in light must also behave as a wave. And this is the foundation of quantum theory, and that it describes both the wave and particle nature of electrons. In order to help you understand this more and more completely, let's watch a few minutes of the clip that we started in class from Nova, the Fabric of the Cosmos.
We can get a pretty good feel for the double slit experiment and how dramatically it alters our picture of reality by carrying out a similar experiment, not on the scale of tiny particles, but on the scale of more ordinary objects, like those you'd find here in a bowling alley. But first, I need to make a couple of adjustments to the lane. You'd expect that if I roll a few of these balls down the lane, they'll either be stopped by the barrier or pass through one or the other slit and hit the screen at the back. And in fact, that's just what happens. Those balls that make it through always hit the screen directly behind either the left slit or the right slit.
The double slit experiment was much like this, except instead of bowling balls, you use electrons, which are billions of times smaller.
You can picture them like this. Let's see what happens if I throw a bunch of these balls. When electrons are hurled at the two slits, something very different happens on the other side. Instead of hitting just two areas, the electrons land all over the detector screen, creating a pattern of stripes, including some right between the two slits, the very place you'd think would be blocked. So, what's going on? Well, to physicists, even in the 1920s, this pattern could mean only one thing: waves. Waves do all kinds of interesting things, things that bowling balls would never do. They can split. They can combine. If I sent a wave of water through the double slits, it would split in two, and then the two sets of waves would intersect. Their peaks and valleys would combine, getting bigger in some places, smaller in others, and sometimes they'd cancel each other out. With the height of the water corresponding to brightness on the screen, the peaks and valleys would create a series of stripes, and what's known as an interference pattern. So, how could electrons, which are particles, form that pattern? How could a single electron end up in places a wave would go?
Particles are particles, waves are waves. How can a particle be a wave?
Unless you give up the idea that it's a particle and think, aha, this thing that I thought was a particle was actually a wave.
A wave in an ocean? That's not a particle. The ocean is made out of particles, but the waves in the ocean are not particles. And rocks are not waves. Rocks are rocks. So a rock is an example of a particle, an ocean wave is an example of an ocean wave, and now somebody's telling you a rock is like an ocean wave. What?
Back in the 1920s, when a version of this experiment was first done, scientists struggled to understand this wavy behavior. Some wondered if a single electron, while in motion, might spread out into a wave. And the physicist Erwin Schrödinger came up with an equation that seemed to describe it.
Schrödinger thought that this wave was a description of an extended electron, that somehow an electron got smeared out, and it was no longer a point, but was like a mush.
There was a lot of argument about exactly what this represented.
Finally, a physicist named Max Born came up with a new and revolutionary idea for what the wave equation described.
Born said the wave is not a smeared out electron or anything else previously encountered in science. Instead, he declared it's something that's really peculiar, a probability wave.
That is, Born argued that the size of the wave at any location predicts the likelihood of the electron being found there.
Where the wave is big, that's not where most of the electron is. That's where the electron is most likely to be.
And that's just very strange, right? So the electron on its own seems to be a jumble of possibilities.
You're not allowed to ask, where is the electron right now? You are allowed to ask, if I look for the electron in this little particular part of space, what is the likelihood I will find it there? I mean, that bugs anyone, anytime.
As weird as it sounds, this new way of describing how particles like electrons move is actually right. When I throw a single electron,
I can never predict where it will land. But if I use Schrödinger's equation to find the electron's probability wave, I can predict with great certainty that if I throw enough electrons, then say 33.1% would end up here, 7.9% would end up there, and so on.
These kinds of predictions have been confirmed again and again by experiments. And so the equations of quantum mechanics turn out to be amazingly accurate and precise, so long as you can accept that it's all about probability.
So again, as we look at that video, we begin to see that the interference pattern developed from the double slit experiment because of the wave nature of electrons. So now the next principle we're going to look at within quantum theory is called the Heisenberg uncertainty principle. This principle simply says that it is impossible to know two things at once. It's impossible to know both the position and the velocity of an electron at any given time. So what the Heisenberg uncertainty principle says, if I want to take a snapshot of an electron in motion, I can see the location of it, but I cannot know the velocity, much like this picture of the NASCAR. So once the picture was taken of the NASCAR, I don't know its velocity, I can't calculate its speed, and I can't even calculate where it's going. Or in the opposite, if I want to calculate the speed of the car, or if I want to calculate the speed of an electron, I have to forfeit my right to know the position of where it's at and where it's going. This is a confusing idea for some of us to grasp, but it's been proven true. That in the electron, we know where we can find it. We can even track its ability to travel, but we can't know both the position and the velocity at the exact same time. So instead of having an accurate picture of where electrons are, we actually come up with what's called orbitals. These are regions where we assume that the electron can exist, and where if we were to take a picture, we would most likely find the electrons to be at. So you might also hear this term orbital referred to as probability orbitals. So when we talk about things like the s orbital, the p orbital, the d orbital, the f orbital here in a second, those orbitals, those shells, those regions are where we will most likely find an electron. But again, its exact location is sometimes forfeited because, again, we want to calculate the speed. So as we move forward, we are going to start talking about the 4 quantum numbers. And I already told you in class, when we talk about quantum numbers, it is best if you think of the quantum numbers much like an address. Our school is located at 1 Trojan Place in St. Leon, Indiana. Well, when I look at an electron, if I want to find the specific quantum numbers of an electron or the address about that electron, I'm going to come up with 4 values that will help me determine where an electron is with the exact position. So we're going to have things like the spin, the magnetic number, the angular number, and the energy level. So these are 4 numbers coming together to make the quantum numbers. They just describe the location or the properties of where an electron is or might be. And again, we can think of this as an address. And the first value we look at is called the principal quantum number. The principal quantum number is in green in the top right of your screen, and that's just the energy level. It's like the overarching area, the overarching energy level where an electron might be found. So I kind of equate it to the state of Indiana, the general region or area. And again, the higher the energy level, the further away from the nucleus we are moving. So energy level 1 would be the energy level closest to nucleus. And as we move further away, we would get up to energy level 7 and even as high as you want to go to infinite numbers. So the next number we look at is called the angular momentum quantum number. This I equate it to kind of like the city you would live in. It tells us a little more information about the electron, but the angular momentum is specific in telling me the actual shape of the orbital. And remember, the shape of the orbital is the probability shape. Where would I most likely find an electron within an atom? So again, the orbital has different shapes. We're going to look at the s, p, d, and f orbitals. And so just to get started, our s orbital is going to be a sphere. The p orbital is the shape of a dumbbell, or I say figure 8 in 3-dimensional. The d orbital is often referred to as an x. And then the f orbital gets a little tricked out. This is just one f orbital, but on the next screen you'll see a few more. But again, what's the angular momentum quantum number? It is just the number to equate what shape an electron is existing in, or what's the probable location of that shape. Now, the next quantum number we see is called the magnetic quantum number. Magnetic quantum number talks about the orientation or the axis in which that orbital exists. Since the s orbital is just a sphere, there's no real magnetic number that we're going to come up with. So that's why it's going to be called 0. The p orbital, though, since it's a figure 8 in 3D, it can actually align itself to the 3 different axes, the z, the x, and the y. We're going to label these numbers as -1, 0, or 1. The d orbital can also have 5 different orientations, depending on which axis or which combination of axes it lines up on. And so those common numbers can be -2, -1, 0, +1, +2. And then, of course, the f orbital notation can have 7 orientations. And again, each orientation can contain up to 2 electrons. Remember, electrons are going to pair up. So my s orbital would have 2 electrons. My p -1 would have 2 electrons. My p0 would have 2 electrons. And my p1 will have 2 electrons. And again, 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons. And that's why you see the varying shades of colors here to represent where there's 2 electrons. In class, I'll walk you through how to get these specific numbers if you want to fill in an address. But right now, we're just introducing the idea of the quantum numbers. And the final part of the quantum number, or the address for an electron, is the spin number. The spin number just indicates how the electron is spinning. We can reference this as spinning to the left or spinning to the right, spinning clockwise or spinning counterclockwise, going to the north or going to the south. Or when we talk about quantum numbers, we choose to differentiate between the two by saying plus a half or negative a half. Again, when two electrons occupy the same orbital, they're not going to be in the same location at the same time. And they will actually be across from each other. So that's why we look at one with a positive half spin and one with a negative spin. So again, our spin here is kind of like the street number. The magnetic number, which tells me what axis is on, is kind of like the street address. The angular momentum, which tells me if it's S, P, D, or F, is like your city. And then the energy level is kind of like the state. And so again, we'll practice this in class, but I hope you find this all pretty easy once you understand the pattern. So again, long story short, our electrons, they have wave-like properties, which we saw by the double slit experiment. The Heisenberg uncertainty principle tells me that the speed and the position of an electron cannot be known at the same time. If we want to study one, we have to forfeit the right to know about the other one. The orbitals are showing the probable locations of electrons, and then the quantum numbers are like an address. They just show me the properties and give me more details about the electrons and their different orbitals. Have a great day.